Assalamualaikum everyone. So my name is JURIANA BINTI. So this is our group member, AFINA, AHMAD KHUSAIRI and RIZKI JAYA. So for today's presentation, we are going to present about PID controller design for quarter car suspension based on model from intelligent system identification. So I will pass to
Okay, thank you, Juliana.
Okay, welcome.
Okay, so this is the introduction for this case study. So this generally a vehicle suspension system perform two major tasks. The first one is to isolate the vehicle from the external road disturbance for the sake of passenger comfort, and the second task is to control the vehicle body altitude and maintain a firm contact between the road and the tire. And the main weakness of the passive suspension that it is unable to improve both ride comfort and safety factors simultaneously. And in this report, we decided to use a semi-active suspension system to develop based on the passive suspension system. And also, the PID controller has a function to adjust the damping coefficient of the variable shock absorber in order to keep the car body always stable. Okay, thank you. We'll pass to the next.
Okay, thank you. So for this problem statement, in this case study, we know that usually passive suspension system are used in common vehicle. So the problem statement was the passive suspension system having the damping and the stiffness of spring is still not given the best performance when accelerating in high speed and having a bumpy road. Why? Because the vibration amplitude that produced from the passive suspension is still high, and it needs a longer time to terminate the vibration. So how do we overcome this problem? So we choose the semi-active suspension rather the active suspension, because the semi-active suspension requires small amount of energy compared to the active suspension. And the active suspension is very suitable to be applied on most vehicle to keep the quality of comfortable on the any road condition, which the stiffness of spring and the damping value that will be controlled and adjusted using the PID controller.
Okay, thank you, RIZKI. So I will continue for the application. So PID controller is an instrument that regulate temperature, to regulate temperature, flow, pressure, speed, and other process variable in industrial application. So control loop feedback mechanism is used by PID, which is in other words proportional integral derivative controllers to control process variable, and it is the most precise and stable controller. So closed loop control feedback is used by PID control to keep the actual output of a process as close as possible to the target or set point output. So this is the example of the block diagram for suspension system that have actuator and sensor, and also the PID controller before the actuator. So thank you.
So okay, so for the block diagram for the PID controller, it consists of three basic controller behavior, which is proportional, integral, and derivative. And for the proportional, or we call it P controller, that gives an output that is proportional to the current error. It compares the desired or set point with the actual value of feedback process value. And the next one is integral. So, or we call it I controller. This is necessary to eliminate the steady error state due to the P controller limitation where the offset between the process of variable and set point always exists. And the last one is derivative. It is used to overcome the problem that could anticipate the future behavior of the error. And for this PID controller, it consists of 3 gain blocks, 1 integral block, and 1 derivative block, and also 1 sum block to total the PID equation. And also having a different value for 3 gain blocks, which is KP, KI, and KD. Okay.
Okay, thank you, Rizky, for the explanation. So now I'm going to talk about the actuator. So the actuator is used to control the direction, extent, and duration of the output of the system. So when the actuator receives a control signal, which is the command, the actuator responds by generating the force or energy to change the system. So for the actuator in this suspension system, it controls the outputs produced by the PID controller, in which the amount of output signals are limited. So as you can see at the bottom here is the actuator with the given actuator with values given in Simulink MATLAB. So next, I'm going to pass to the next presenter.
I think this part should be...
Okay, thank you, AFINA. Sorry. Okay, for this, now I will explain about the plant system. So this figure is show the quarter car lump parameter model. So when we talk about the system, it involves the equation. So this is the equation. H1 equal to Z1 over US, and displacement of the quarter vehicle body mass, or Z1, is the output, and the UT is considered as the input. So we will use the MATLAB to generate this. Just input the equation into the MATLAB and see the result from there. Okay, next.
Okay, so for the next block diagram is sensor. So for sensor, sensor can convert the measured physical action into an electrical equivalent and process it so that it will be easy to send and further process into the electrical signal. The sensor can indicate whether or not an object is present, which is in binary, or what measured value has been achieved, which is in analog or digital. So this is the sensor that we use, which is this is the from the slide. There are figure that sensor that we use. So thank you.
So, okay, the mathematical model for this experiment, which is a PID controller. So the transfer function for the PID controller is found by taking from the Laplace transform equation. So as I mentioned before, there is a 3 constant value that apply on the 3 different gain, which is Kp, Ki, Kd. And this is the equation of the Laplace transform equation that we use to find the transfer function for the PID controller. Thank you.
So now I'm going to be explaining about the actuator transfer function. So in this system, a first order model of an actuator is used. So the actuator device with the time constant tau equals to 1 second is employed. So the equation of the transfer function of the actuator is given by the formula of Hs equals to 1 over tau s plus 1. So next.
Okay, so this is for sensor. So the transfer function for sensor, in this case, we assume the sensor is in constant 1. So sensor also known as feedback loop in this diagram system. So.
Okay, for the system, I will explain how I got the equation. So this is the general equation, and this is the what we call the meaning for each unknown, where the m consider the mass and m2 the mass and k1 is because you can read by yourself. Okay, next. Okay. So based on the general equation or the equation one, the all the initial consider being zero, and I apply in the Laplace transform to equation, and I will got these two equation. So based on the system of equation one, we can determine that two transfer function, which is these two. Consider this displacement of the quarter vehicle mass or Z1 as the output and the Z2 as the input. We will got this the fourth equation. Next. And after that, I will replacing the fourth into the third equation. Give the first transfer function, this one. So for this, I will consider Z1 as the output and the Z2 as the UT as the input. And after that, uh, okay, this is the no, back slide before. So from equation 2, equation before, we extract Z1 as this Z1 equal to Z2 and so on. Okay, next slide. After that, I am replacing the fifth equation into the third equation. Give this one the first transfer function. And okay, next. Okay, this is the parameter that we use to input into the MATLAB. You can read from that. Okay, that's all.
Okay, so this is what we do in MATLAB. This is the block diagram that we use in Simulink MATLAB. So as you can see, we put the PID and then actuator and then the system. So there are two systems there are actually three systems in this scope that we do. So the first one is from the first generator, the input, and then we do the PID controller, the suspension system with PID controller, and the last one is we do the suspension system without the PID. So we can see the difference between these three output. So next slide. So this is the result that we get from the Simulink. So as you can see, suspension system without PID is the red color one. So it is the output is higher from the suspension system with PID. So you can see that the blue line is the system with PID. So it's more better than the suspension without the PID. So the yellow one is the first generation generator, which is the input that I choose for this system. So next slide. So this is the result that we get from the graph. So you can see that the value for maximum peak amplitude, maximum value, peak amplitude, and maximum time for PID is decreased from the without PID. So which is better for the suspension system. So but the RISE system increase. Yeah. So I think that's all for result. Next presenter will discuss about the discussion.
Okay, thank you. So for the discussion, as we know that we use the PID controller for this simulation using a PID controller which has modified value of KI, KP, and KD. And the value differences that we used was to observe the effects of PID controller that already used on semi-active suspension to achieve the desired result. And also the graph that we already seen is to compare the result of suspension system with the PID controller and without the controller. And also from the graph, we can see that PID controller has a smaller wave or more stable compared to the system without PID controller that has slightly bigger wave that obtained from the simulation conducted. Okay, the next will be continued by my friend.
So based on the graph, it shows that the suspension system that has the PID proved to be more efficient compared to the suspension system without the PID. So this is because the PID controller uses the present, past, and future errors to calculate the appropriate actuator commands. The PID control system is able to give better performance for the minimization of the maximum displacement of wheel mass, and with the implementation of the PID in the suspension system, the vibration amplitude that is produced in the chassis system can be controlled, and the time required to terminate the vibration is minimized. Next, I'm going to pass to the next presenter.
Okay, as conclusion for this project is, I don't know why it's not appear, but
Okay.
As conclusion for this project, it can be seen that simulation of the PID controller was successfully simulated using MATLAB Simulink. It is to compare the suspension, the vehicle that with suspension and without the suspension that with the PID and the without the PID. After conduct this experiment, we know that the suspension that has the PID is more efficient compared to the suspension without the PID. I think that's all for our presentation. Thank you.